Welcome to an auxiliary lecture for Mean 315 Principles of Thermodynamics on electric motors. And you'll notice that on the title here I say electric motors and generators, since basically a generator is just the opposite of a motor, and you'll see us describe that in today's lecture. Okay, so first of all, we've drawn this a few times in lecture, and I'm going to go over a few more details here just so that we're all familiar with everything and are on the same page. But let's go ahead and draw what an electric motor basically looks like as best that we can, right? So we have essentially this box or this cylindrical device, and we have two electrical terminals, right? One for the positive, one for the negative, or hot and common if you prefer. And we have a current that flows through this terminal, and then of course between the two terminals there's some voltage difference, right? So there's a voltage difference V between these two terminals. And then we also have a spinning shaft. And so this spinning shaft has some rotational speed N, which is in units of revolutions per second. And it's also producing some torque, which has units of Newton meters if we're in the metric system, or foot-pounds if we are in the British system. So this is kind of a schematic of what a motor looks like, right? And the other thing that we have to note is, this motor, right, generally can get hot because it's operating with rotating parts and current flowing through it, and so there's friction and electrical resistance, and we know that all of that energy basically dissipates from the system as some kind of thermal energy, right, which is the heat transfer. So we have some thermal energy that's transferring from the system into the surroundings. And that's just a fancy way of saying that, that the motor is trying to keep itself cool, right? It's transferring thermal energy into the surroundings basically as a means to cool itself. Otherwise, it would just get very hot and melt and start to seize. So we can then start to take this information that we have here, and we can transfer this now into a thermodynamic control system. And so we can go ahead and draw that down here, where again we have our motor, and now we have some electric work coming into our system. So this is W dot electric. And again, I always draw everything in the positive orientation, which means that the arrow, if the electrical work were leaving the motor, we're exiting the motor, going from the motor into the surroundings, then this would be positive. But I know that I am supplying the motor with electrical power, and so the number here will actually be negative, right? And my rotating shaft, well, this is basically shaft power, so I have shaft power that's coming out, and now that is in the positive orientation, right? So this is a positive number. And then, of course, I have my heat transfer, and so I represent that as Q dot. But of course, I know that that thermal energy is leaving the control system, and so that would also be a negative number like the electrical power. Now, my control system itself, right, will have some kind of, different properties, right? There will be a motor temperature, and the energy of the motor and the entropy of the motor. And what I do is I make the assumption that this is all steady state, right? And so if I make the assumption that I've brought the motor up to temperature, and T motor is no longer changing with time, the energy of the motor is no longer changing with time, its entropy is no longer changing with time, then I can assume that my control system is steady state. Okay, well, let's provide a little more definition to what we mean by electric work, or electric power to be more precise, and shaft work, right? And so we can essentially define this electric power as follows, and this would be if we want the electric power to be in units of watts, right, which is a unit of power, then the electric power is simply equal to the voltage in volts times the amperage. in amps, or the current. And that's nothing more than a variation of Ohm's law. If you remember, Ohm's law is a relationship among current, voltage, and resistance. We can essentially modify that so that we get it in terms of power, in which case power is simply voltage times current. Now, the other important piece of this, of course, is the shaft power, right? Oh, excuse me. Let me just throw in here, too, before I forget, the fact that this is all negative based on the way that I've drawn the way that I've drawn my electrical work. Since I've oriented the positive direction coming out of the system, I need to make sure that that electrical power is in fact negative when I plug it into the first law equation, which will be coming up shortly. Okay, so then the next work term that we have, of course, is the shaft power. And so shaft power is has the following units. It is basically 2 pi times the rotational speed, n, in revolutions per second, times the torque in Newton meters. And if you use these units, then you will have units on the left-hand side of watts. If you are using foot-pounds, then you can still keep your revolutions per seconds the same. Your torque, however, will be in foot-pounds, in which case you then need to look up a conversion to go from foot-pounds per second into something like BTU per hour or BTU per second, whatever, or horsepower, whatever units you want to use. And I refer you to the conversion factors that are on the booklet of the back page of your booklet to learn more about that. And there's an auxiliary lecture on English units if that interests you. Okay, so it's a little bit interesting to know where this equation comes from, right? We have this 2 pi times the speed of the motor, the speed of the shaft of the motor, revolutions per second, times the torque of the motor. You know, why is there this 2 pi in there? You know, why is there this relationship between n and t, the speed and the torque? Well, where this comes from is basically the following. Suppose I look at the bird's eye view of the motor shaft, right? So suppose, or suppose not the bird's eye view, excuse me. Suppose I look into the motor shaft, right? And so this circle here represents the motor shaft, okay? And what essentially I'm doing when that motor shaft transfers torque is I can essentially perceive that torque as being a force that's right on the surface of the shaft, okay, right where I drew a dot there. And what makes it a torque is that I have some moment arm, which just so happens to be the radius of the shaft, right? So I have this force that's applied to the outer surface of the crankshaft, and that makes sense, right? This is where I might attach a fan blade if my motor is spinning a fan, or a belt if I'm connecting it, or a chain, or some other kind of attachment that some kind of transmission device that transfers the rotating shaft power to some other element that I want to deliver. So there's some external force that's applied on the outer surface of the shaft, and because the outer surface of the shaft is a distance r, the radius of the shaft, from the center of the axis, that then creates the torque, right? So the torque is the force times the radius. Okay, so just hang on to that. We'll come back to that in just a moment. So, of course, we know that this shaft, right, is spinning at some kind of rotational speed, n. So this is revolutions per second. And so we can kind of track the rotation of this shaft, right? And say that, after a quarter turn, right? If I follow that dot, my dot is now here, right? So this is the application of the force. And then if I do another quarter turn, well, now the dot is down here, and this is where my force is. And then if I do another quarter turn, And my dot is right here, right? And this is the application of the force. And then finally, I get to my final rotation, and I'm back up at the top again, right? So this is my application of the force. Okay, well let's take a look and see what actually happened here, right? If you notice, what we basically did is we went from, let me just clean this up a little bit here. We went from a position, right, to a different position, some initial position to a final position, and that's one revolution of the shaft, which if we think about what that dot tracked out, right, if we think about how that dot mapped this out, right, if we had this dot on, say, a roll of paper and we had some ink on that dot, then and it were to map out a linear distance, well, for one revolution, that linear distance is just the circumference of the crankshaft, which is 2 pi r. And if I further think about this and I say, okay, well, I had an application of force and I moved that force a certain distance, well, that's nothing more than a work term, right? So work is force times distance. And so my distance was 2 pi r, right? The distance that was mapped out by that point. And so my work for one revolution is 2 pi r times the force. Okay. But I don't have just one revolution, right? In fact, I have multiple revolutions, and that's now where my rotational speed comes in. Essentially, if I want to have this on a work per unit time basis, what I need to do is I need to then, so work, W dot, of course, is work per unit time. And since I have now work has units of, say, units of work, which in the metric system, for example, would be, say, Newton meters, and this is per revolution, right? Then I need to, in my denominator, I have units of seconds. Well, I have to multiply my W times something that will eliminate those revolutions and introduce seconds. Well, that's what n is. My rotational speed has units of revolutions per second. Okay, and so my W dot basically becomes the following. I can say that W dot is equal to W, which has units of Newton meters per revolution, times n, which is revolutions per second. And my revolutions cancel, and I'm then left with units of Newton meters per second. Remember that a Newton meter is also a joule. And so then I have joules per second. And then, of course, I have a very specific definition for what a joule per second is. That is exactly equal to a watt. And again, you can do the same argument if we're doing British units here, where you'd have feet pounds per second and such. But you get the idea that we're trying to convey here in terms of why n appears in the expression and why n and torque appear in the expression. Okay, so actually, if I look and if I start to now piece this together, I'm not quite done just yet, right? So what I have is I have now that my work dot W dot is equal to W times N. And if we remember what we said W is, we said that W is 2 pi times the radius times the force. And then we have this N that's also in here. But then we recall that the torque is R times F. W dot into the form that we're familiar with, 2 pi times the torque, right? This is our torque here, times N. And so that's where the expression for shaft power comes in. Okay, so now we can take this information and we can go back to our control system, and we recall that we had different heat transfers and work transfers and such, right? If we go back up one more page, we have W dot electric, we have W dot shaft, and we have Q dot. So we can now assemble our first law, right? And so we're going to use our first law equation for our steady state analysis. And so what that gives us is the following. Our first law then becomes the following. We have Q dot plus the sum of our energy in, M dot I, times HI total. And this is all equal to W dot plus the sum of our M dot E times HE total. Okay. And when we dissect this, we see right away that this term is going to be 0 because M dot I is equal to 0. We don't have any mass transfer into the system. And likewise, this term will also be 0 because we have no mass transfer out of the control system. And so our first law then simply becomes that Q dot is equal to W dot. And so we have, in fact, two work transfer terms. Our first work transfer term is, of course, the electric work, right, or the electric power. So this is W dot electric. And then we have the second work transfer term, which is the shaft power. And so we just need to, and we have expressions for both of these. We can say that Q dot is equal to the electric power, which is negative VI. And then we have plus the shaft power, which is 2 pi times the torque times the rotational speed N. So we can use the first law to determine what that heat transfer rate is if that's something that's interesting for us. The other thing that's important to define for an electric motor or generator, which again we'll get to in just a moment, is the efficiency. And so of course we recall that efficiency is simply defined as what we get divided by what we pay for. Okay. And in the case of an electric motor, what we get is the shaft power. And what we pay for is the electric power. Okay. Okay, so it's useful at this point. We've talked about efficiency a few times, but we've never really fully dissected, what the maximum efficiencies will be. And this is going to be a prevailing discussion all semester long. But a very realistic question that we can ask ourselves is, what is the ideal or the maximum possible efficiency for an electric motor, right? What numerical value could this be? Well, because we're going from electric work to shaft work, in other words, it's just from one type of work to a different type of work, the maximum efficiency can be 100%, right? So what a motor does is a motor converts one type of work energy and that one type is, of course, electric work, into a different type. But still work energy, a different type of work energy. And in this case, that's shaft work. So we have work to work, and so we have essentially an opportunity for there to be 100% work transfer, right? So in the ideal case, we can in fact do this. Now, we're going to be talking about entropy all semester long, and the reason why, so we can, conceptually it makes sense why we can say that something that takes one type of work and converts it into another type of work, that we can have ideally 100% efficiency. But we can also look at this from a second law perspective, right? And if you remember the second law equation, the second law equation is essentially states the following: ds is equal to q dot divided by t plus the sum of our m dot I times Si minus the sum of our m dot E Se plus entropy generation. Okay, and we can of course say that we have no work transfer, right? Or excuse me, no mass transfer. So m dot I is equal to 0. This term drops out. We're talking about this for the electric motor. And m dot E is equal to 0. So this term drops out. Okay. And if we say that our motor is ideal, then that basically means two things, right? First of all, it means that there are no heat losses, so this q dot term is equal to 0. And you may be wondering, well, why can't there be a heat transfer for it to be ideal? Well, think about where that q dot is how that q dot is generated. It's generated by friction in the bearings, by electric resistance in the windings, by wind friction, aerodynamic losses as the motor has windage losses. So all of these are losses, right? These are all irreversibilities. And if you have any questions about that, you can refer to the irreversibility auxiliary lecture. But the point is that this q dot here represents all of the losses that are in that motor system. So if we want to create the ideal motor, we have to perceive there being a q dot equal to 0, there not being any losses in the system, okay? Any heat transfer losses, excuse me. So that's the one, is that q dot has to be equal to 0. And the second thing, of course, is that this entropy generation term also has to be equal to 0, right? And again, for more information on that, refer to the irreversibility auxiliary lecture. So with these two terms now equal to 0, when we look at our second law equation, basically what we see is that for the ideal case, ds is equal to 0 for the ideal situation. And this is an important concept, because what that means is that for ideal work transfer, there is no entropy transfer or no entropy change. And if you have no entropy change, then you can't degrade the quality of your energy. So the quality of the energy stays the same. And if your quality of energy is staying the same, then you can have an efficiency that approaches 100%. Okay? Cool stuff. Very conceptual, but very important, because what this allows you to do is recognize that different systems will have different efficiencies based on how they handle entropy, right? It all comes down to entropy. If the system is transferring a lot of entropy, then it's going to have an efficiency, a maximum ideal efficiency that is less than 100%. Okay, very quickly, let's just very briefly discuss what a generator is. And this is pretty straightforward, simply because a generator is the opposite of a motor. So if a motor takes electrical power and converts it into shaft power, what a generator does is it takes shaft power and converts it into electricity, right? So what does a generator look like, right? We can go ahead and draw our control system just like we did for the motor. And so now what we have is again, a spinning shaft, right? So this shaft has some kind of rotational speed n with revolutions per second. And we're putting a torque into that shaft. And as a result of that, what the generator does internally is it produces a current at some voltage potential V, right? So this is how a generator works. And like a motor, right, generators can get hot, so you can have some kind of, thermal energy loss here, right? So this could be T hot, and there can be some thermal energy transferred to the surroundings as a result of that motor being hot and needing to cool itself in the surroundings. So thermodynamically, we represent this basically the same way as a motor, right? So we have, again, our control system, and we say that the temperature of the generator is constant, right? We're going to make the assumption that this is steady state. And we have our shaft power, W dot shaft. And now, because this is going into the control system, this is going to be the negative quantity. So this is negative 2 pi times the rotational speed times the torque. And then what is positive is our electrical power, right? So this is now a positive voltage times current. And then, of course, we have our Q loss. And this is going to also be a negative number because it's going to be leaving the control system. Okay, so first law, pretty straightforward. You start with the steady state first law. I won't go through the whole derivation because it's just the same as the motor. And basically, it looks the same, so that SS there stands for steady state. And so our first law basically tells us that Q dot is equal to the electric power plus the shaft power. And then when we go ahead and fill in our known values, of course, the electric power is just the voltage times the current. This is what's coming out. And then we have, of course, the shaft power, which is negative 2 pi times the rotational speed n times the torque that is being transmitted, T. Okay, now the one thing that we do have to pay attention to is how efficiency is defined, right? So efficiency is going to be defined a little bit differently than it was. Conceptually, it's still the same definition, right? So we can still say that efficiency is what we get divided by what we pay for. And so what we get now from a generator is W dot electric. And what we pay for is shaft power. Okay? And again, we're going from one work transfer to another work transfer. Ideally, work transfer does not transfer entropy, right? That's what our second law equation told us. And so our ideal generator efficiency can be 100%. It can absolutely approach 100%, no problem. Okay, so that's it for the auxiliary lecture of electric motors. As always, if you have any questions about anything, please feel free to contact me. Otherwise, enjoy your day. Bye-bye.